Okay, welcome everybody. Last week we did reference counting, and today I want to do cycle collection for reference counting, generational reference counting. I want to talk about state-of-the-art collector based on reference counting and things that we've done. And whatever I make it after that, it will be great. There is a third exercise, your last exercise that I will try to put in during the break. It's smaller than the previous exercises because it's the last 2 weeks or 3 weeks, 3 weeks, and I know everybody is very busy, uh, but it is an exercise. So there is today where I got a message that we're starting the lecture evaluation, that I want to encourage you to take part, to evaluate me. I want to know what you think. I know that most of you think, oh, he knows what I think, it's okay or it's not okay, but I don't know what you think, and I always get interesting responses, and you can write. I'm reading whatever you write, or if you want, you can just grade me, and that's fine. But please do. It will be good for me and for the future students who want to see what you thought about it. So we're going to most of the lecture today is going to be about cycle collection. So as you know, reference counting cannot reclaim cyclic structures, and this is like a major job. Like I cannot collect everything using my collector. And just to say what it is, a garbage cycle, it's unreachable, strongly connected component. Okay, it doesn't have to be a simple cycle. So if I don't know if you have whatever. Um, Yeah, this is a strongly connected component. If you can reach any node from any other node, then it's a strongly connected component, and you cannot reclaim it. And of course, if this is an unreachable cycle or SCC, and there is something that is reachable from it, then you cannot reclaim that too, because the reference count of that will also never drop to zero. So all of this will have positive reference counts, and also whatever depends on it will have positive reference counts. So you'll not be able to reclaim any of that. Cool. So we need to do something. Here is an example. So these slides were made when this was in the beginning a seminar, and students did beautiful slides. So I'm using them. It's not mine, but I'm enjoying them. So first you can see here's a cycle, like a strongly connected component. Now it's reachable from the roots. And if I change this pointer, it will become unreachable. And you can see that if I update the reference counts, then this thing has positive reference counts. It will never change. The program cannot touch it anymore because it's unreachable, but still I cannot reclaim it with reference counts. Okay, so what in the beginning they suggested to do was just to you use reference counting until you see that the heap blows up and you're not reclaiming enough. And then what you do is you run a mark sweep or a copying collector. These collectors do not even look at the unreachable space, they just reclaim it. So it doesn't matter if it has cycles or if it doesn't have cycles, it will reclaim whatever is not reachable. So they will reclaim all the cyclic structures. And another thing good that they do is that they can get stack reference counts updated. So if you remember, we wanted to have a limited field for the reference count, like maybe most objects do not have more than one or two references, and so and very few have more than 16. So you want to use 4 bits to keep the reference count, and if something has more than 16 references, then it gets stuck, and then you cannot update the reference count anymore, and you cannot reclaim it. But if you run a garbage collector, and this has only 3 references now, you could, through the garbage collection, the mark sweep garbage collection, you can update all these reference counts that got stuck but now are lower. So, and we talked about it when we last week when we talked about stuck reference counts. You can use mark sweep to get rid of all the stuck pointers. So a tracing collector can do that. It's good to use it. And these are the benefits. You can reclaim circular structures and you can use small RC fields and not get objects that you cannot reclaim. But if you do that, you have two garbage collectors in your system. You have a mark sweep garbage collector that you run once in a while, and you have a reference counting garbage collector, and you have to debug and maintain all of them. If you make changes in the language, you have to update them both. It's like two major components in your system that you have to worry about all the time. Companies do not like that. So it is a problem. To do that, we want to do something within reference counting that can work with cycles. Okay. So what we'll do, we'll talk about the basic observation, local mark scan, which is the basic algorithm. It's very basic, but it will be the one that will be used until today. And then we'll talk about how to do it more and more reasonable, because the original one is very, very slow. So Linz went in a lazy manner, and then Bacon and Rajan had some improvements, and you'll see more improvements, and we'll talk about them all. There are recent papers on cycle collections that have not really, that they're not cooked enough to talk about them. They're very slow. They kind of have weird advantages. And there is also work here on this topic. Last year, when I ran this course, one of the students came with an idea that is nice. And he just started the master's, and we're working on that. So we'll see how that goes. So there are more ideas than what I'm talking about in this lecture, recent ideas, but all of them are not well done enough to be taught in class. So just know. So the basic idea by Christopher in '84 is that you can only get unreachable cycles if the reference count is decremented not to zero. So if reference count is decremented to zero, it's not a cycle, you can reclaim the object, we're done. If a change of a reference count is not going down to zero, then it's possible that I just made a cyclic structure unreachable. It lost a pointer, the last pointer to it was lost. You know, many times when the reference count is decremented to non-zero value, it's not a new unreachable cycle. But when there is a new unreachable cycle, there has to be a decrement of a reference count to a value that is not zero. So it goes one way, but not the other. So so having this observation, let's look at some terminology. So I will look at an object. So this object, perhaps its reference count got down, but not to zero, as it is here. And it has a subgraph. What is the subgraph of an object O? It's all the objects I can reach from O. So everything in this triangle is reachable from O. A is not reachable from O. It's outside its subgraph. So each object has a subgraph. And I will call external pointers pointers that point from outside the subgraph to inside the subgraph. Okay? This is an external pointer. An internal pointer is from within the subgraph to within the subgraph. Okay, so internal pointer and external pointer. Could there be the other direction, like an external pointer? Right. Exactly. If there would have been a pointer from here outside, it would be inside the subgraph. It's reachable from O. So there can only be external pointers that point from outside to inside. That's the only possibility for an external pointer. And so these are the three terms that we have to remember. And now there is the second observation that was done by these guys, Martinez, Watchen, I cannot say that, and Linz in 1990. So they say that if I look at the reference counts of these, and all the reference, so if there is a reference count that's only due to internal pointers, then it is not pointed from outside. So, for example, this guy has a reference count 1, and there is one internal pointer pointing to him. So its reference count is originating from internal pointers. This guy has reference count 2, but there's only one internal pointer pointing to it, so it is referenced by an external pointer. Okay, so this is the basic observation, and if all the reference counts of a subgraph are due to internal pointers, then the entire subgraph is unreachable from the outside. Okay, if I can look at all the reference counts and check all the reference counts that are due to internal pointers, and it's all the same, so all the reference counts come from internal pointers, then this thing is not reachable from the outside. Okay, this is the main observation, and this is how the algorithm. This is what the algorithm is going to check. Okay, so this is actually an observation due to Christopher. Is he mentioned? He's not. Okay, he's not mentioned here. It's due to Christopher in '84, and these guys, Martinez et al., made it an algorithm for a specific subgraph. So okay. So let's do an algorithm. The algorithm will say if someone's reference count is decremented to a value that is not 0, I will check it. This is a guy whose reference count was decremented. It's a candidate for maybe it is part of a cyclic structure that is unreachable. I will check it. I will go down its subgraph and check if there is any reference count that is not represented, does not come from internal edges. So this is going to be the goal. Okay, so what I'm going to do is I'm going to, maybe I have here an edge that was changed, a pointer that was changed, and the reference count here was decremented to something that is not 0. So this is a candidate. Now, the subgraph of this vertex, like the objects that are reachable from it, are exactly A, B, C, and D, like in this rectangle. And I'm going to check if this is an unreachable cycle. So how will I check it? I will reduce all the references that are due to internal edges that are inside this graph. And I will get this, what you see here. These are the reference count when I ignore all the internal edges. And now I can see, if I look at that, I will see that here I have an internal, I have an unreachable cycle, and here not, because this is still 1 after I made all the reference count only represent external edges. This remained 1, so there is an external edge pointing to it. And so whatever is reachable from that is not unreachable. So this guy is reachable. And the rest is unreachable. Yeah. To tell if you're reachable, it's a challenge. How can you know? So if I'm decrementing this, it is reachable from here, right? But I don't know if and it could be a big. Somehow you want the right barrier to mark objects that are reachable. It is a problem because it's, there is a long linked list, right? And at some point I unlink half of this list. How will you know that all of them are unreachable? It's the main challenge of garbage collection. I want to understand reachability dynamically all the time. If I could do what you're suggesting, it would be a great new algorithm, but I don't know how to do it. Yeah. Yeah, the propagation will take like linear time, and then my right barrier will be too expensive. Yeah. Okay, but this is understood. Okay. Yeah. Yeah. This is like the root. This is the why is this the candidate? This is the candidate because it has lost an edge. Or you're asking what's the internal edges and why this is not an internal edge. For me, only what's reachable from this is the subgraph, and only edges from within the subgraph to within the subgraphs are internal edges. That's how I define it, and that's good for understanding if it's not reachable from the root. Okay. Yeah. When I do this trial to see if this is an unreachable cycle, I do linear time of the subgraph. I don't know if the subgraph is large, then I lose a lot of time. If it is small, then I'm fine. But we haven't gotten there yet. It now seems, I agree with you, terribly inefficient. Whenever I change a pointer, someone, I may need to traverse the entire graph for that. That is not good, and I will get to that in a few slides. So it's an excellent question. So the basic algorithm, when an RC of an object is decremented to non-zero, I perform 3 local traversals of the subgraph of this candidate. And I hope the local is small, but I don't know. So I update the RCs to reflect only external pointers. I remove all the internal pointers from the counting. I restore the reference count of externally reachable objects. Now I know who is reachable from the outside. I restore all the reference counts for those, and I reclaim all those that are not externally reachable. Okay, so let's look at the implementation. Yeah. Right. That's part of the algorithm. So it was said very high level, but here we'll do it seriously. Okay, so I want to. So this one, object A, was decremented to a non-zero reference count. So this is my candidate. I'm going to traverse his subgraph and see what happens. So the first thing is mark. I want to have RCs reflect only external pointers. And I also want to mark all these nodes, all these objects as gray. So I'll do both of them in the first traversal. So first I look at the candidate itself and I make it gray. And then I go over all his descendants, all his immediately reachable nodes, which is only this. And I'm going to traverse from them. I'm going to first decrement the reference count. This is an internal edge. Each edge that I encounter is internal because I'm only traversing the subgraph of the candidate. So I want to reduce this to 0. And also it's black, so I haven't seen it yet, so I'm making it gray. Okay, I'm traversing all this subgraph. This is the first time I reach B, and so I make it gray. And I also will recursively traverse its children to decrement the reference count and make it gray. So basically, I'm done with that because it had only one child. So let's go to the new one that I have to traverse. This is B. So B, when I look at it, it has one edge back to A. So I have to decrement the reference count of this edge. And I don't have to traverse A because it's already gray. I've seen it already, so I don't have to traverse its children. Now I go to the other child, which is C. I have to decrement the reference count because this is an internal edge. And I have to make it gray because it's black. So I do that, and I'm done with B. I've seen both its edges. And now I'm going to look at C, which is the new one that has to be traversed. And it has, and I have to traverse its children. So it has one child. I have to decrement the reference count of this. And because it's black, I will mark it gray and add it to the queue of those that have to be traversed. So I mark it gray, decrement the reference count, and I'm done traversing this one because it has only one child. So I go next to this guy to traverse its children, and I see one child, and so I have to decrement the reference count. I don't have to add this to the list of nodes to be traversed because it's already gray. So let's make it 0. And basically, I'm done traversing all the nodes. Everyone is gray, and all the reference counts do not reflect internal edges. So this is great. This is the mark. After the mark, all subgraph is gray, and all reference counts are only due to external edges. Okay, so now I go to the second phase, which is scan. What I will do is I have to, if this one is greater than 0, then it has an external edge and it's reachable. If it's reachable from outside this candidate cycle, then I have to mark it black again. I have to mark all its descendants black, and I have to restore reference counts from these two objects that are going to stay in the heap. Okay, so I'm starting from this, and I see that it's 0. For me, if it's 0, I'm going to mark it white. It's different from the colors we had in the tracing algorithms of Mark Sweep. We don't start with white and go to black if it's reachable. All the objects are black in the beginning. I'm scanning only part of the graph, and I'm going to make it gray, maybe white, and back to black in the end. Everything will be black at the end. Okay, so this guy seems unreachable. It is 0. So I'm making it white and going through its children. So I'll go to this child and I see it's gray, so I'll mark it white because it's also unreachable. And since it became white, I have to traverse its children. So I will look at this. I have to do nothing because this is also white. And I go to this and I have to make it white because it has 0 reference count. And so I have to traverse this. I finished with this. I traverse this. I go here. And this one has a reference count larger than 0. So it is reachable from outside the subgraph. So I'm making it black again. And I'm going to restore the reference counts of all its subgraph. So I will now go from it. I will scan black all its subgraph. So I'm going to its child. I see it's white. I will make it black and restore this reference count. And I'm done with this. I will go to this one. I have to look at its children. It has only one child. So I have to restore the reference count for that edge and make this 2. And it has no more children. So I'm done. I've traversed all the subgraph, made some of it black. Just twice. So it may be the worst case that can happen is that I go traverse everything white, like a huge number of objects, and then at the end I see that it's reachable and I have to go back and mark everything black. At the worst case, it will be twice. Yeah. Yeah. So the scenario is I have D and C, and from C there is, and this is a cycle, from C there is a long, long line, and so I'm coming from here somehow, here through this A and B, and I'm marking these two white, and then I'm marking this white, and I don't go to D, who is black, but I'm going to all these white objects arbitrarily, but I only visit them once, right? And then I mark them all white, and then I go to the second child of C, and I discover it's black, and then C is black, and I have to go through these and mark them black. Where do you want this? Once it's black, you don't touch it anymore. I will need to traverse this, but C will not be traversed twice as a black object. No, no, no. So C will have, one for this, one for this, one for this. It will have three. Right. So all of these have been traversed, and if I find that there is a new black object, and like I had two, and I move it to three because of this edge, I don't need to change the reference count of these. So maybe I will traverse a very long list, marking it white, and then I'll discover that I have to mark it black. But this will happen once for whitening them, once for blackening them. So, in general, it could be a huge graph with lots of, things that are above zero, and you want some methodological way to work through them. Um, but you're right that you could remember all those that were above zero, and you could start marking black from them. Actually, there is. I will talk about improvements. One of the improvements is like that, but a bit different. It's interesting to think about it if it will be better than the improvement that they've done in the past or not. Yeah. Yeah. I did it B, but there is B there. Let's do E. Is yeah. But it will only change the reference count of E and C, not the reference counts. All of these will have reference counts. If this is, I don't know, maybe one, whatever you add to C will not change that. I will change the reference count of C as many edges as touch C, right? But I will not traverse the list again. Yeah. For each edge that enters a node, I will have to change the reference count for this node. That's always. Right. If you recall the analysis of DFS or BFS, you say that it's O of E, it's the number of edges, because you look at how many edges you touch, and that bounds, your traversal. And it's also here. For each edge, you have to work. Right. The reference count of each node depends just on what's the one. Right, touch it, not if maybe C has a huge number of reference counts of references, and so its reference counts is huge, but the others ones have one reference count, and I don't have to visit them again. Yeah, yeah. So the way it was initially suggested, the program itself, it's not concurrent, nothing, it just changes an edge, like it was the 80s or 1990. You change an edge, and then you just traverse the local graph that's reachable from it 3 times, or maybe 4, if you're unlucky. So yeah, this is not this doesn't make sense in terms of the efficiency, but we'll go on. But you're right that we need to think about better ways to do this. But the basic algorithm is this. This is the algorithm, so it's very important to understand it now because we'll just work with it all the time. Okay. We have this? Okay, cool. So the last traversal, the third traversal, I start from here and I collect the white. So I go through, I do a traversal, I start with this, I go to this, I mark them, they are white in the third traversal, they can be reclaimed. And I go down, when I get, okay, so, wait, no. I don't know if I want to go. No, this will be too painful to go through the entire thing. But let's just get the algorithm. Okay. Okay. So there is no going over all of them. But if I go from here and I traverse it, DFS, BFS, wherever you like, then I will find out which are white and which are black. All the whites can be reclaimed. The blacks are already okay. They fit the heap. Their reference counts of their children are updated. Everything is cool. We can just reclaim the white and proceed. Okay, this is the algorithm. 3 traversals. In the first, I make everything gray and I decrement the reference counts of internal edges. In the second, I mark white all those that are unreachable and black all those that are reachable, and I fix the reference counts for the reachable objects. And in the last one, I just reclaim the whites. That does it. Okay, cool. So I want to show this code just to show you that it's very simple. It's not like a complicated thing, very, very simple. So when you do a reference count and some object loses a reference count, like it's decremented, if it goes to 0, you do the things of reference counting. All its children, you recursively reduce the reference counts and so forth. But if it's not 0, what you do is you do these 3 scans, mark, scan, and collect white. And let's look at how they look. So mark is very, very simple. If the color is black, so you haven't worked on it yet, it's the first time you see it. So you make it gray. And for all its children, for all edges that go out of it, you reduce the reference count to reflect it's an internal edge. And so you don't want to see these reference counts. You decrement the reference counts for all the edges that go out of it. And then you just recursively look for each child, you do this. So that's all the marking phase, the first phase. If it's okay, we'll move to the scan phase. Now everything is gray, so everything is gray, and the gray non-zero reference counts means that there is an external reference, and it and all its children are reachable. So what I do, if the color is gray, I haven't touched it yet, I haven't worked on it yet, and if the reference count is larger than 0, then it is reachable, and I go to something that I will soon tell you about. It's called scan black. I mark it black and all its children, and I restore the reference counts, and I do whatever is needed to return it to the graph. Otherwise, I make it white, and for each of its children, I call this again for the child to see if it can be marked white or it needs to be black. So I still need to tell you how I scan black. And this is again very simple. If I see a new child that is not black yet, then I color it black. And for all of its children, I restore the reference count for this pointer that I'm now looking at. And then I scan black the child. So recursively, I go to all the children. And so all the children will become black and with reference counts updated to reflect the black objects. Okay? So this is the scan phase. It scans, it does everything white except for objects that have reference count larger than 0, and then it also goes to their children and marks them black. Okay? And the last phase is collect white. So after scan, subgraph contains only black and white objects. And so I just go to the candidate and I look at its, so it's of course, hopefully it's white, otherwise I'm done. But if it's white, then I color it black I'm going to reclaim it, but I give the allocator objects that are black so that they can fit in the normal graph of the heap. So I mark it black before I reclaim it. And then for all its children, I try to collect them also, if they're white. If they're not white, that I'm going to get to this, if they're not white, I don't need to look at them at all. Okay, and then I just reclaim it. I put it in the free list. So this is the entire algorithm. Yeah.
I have a question regarding the right barrier I asked about before. If we added and the right barrier, if the root itself pointed to an object, we would just mark it blank, and then it would save us time when we did the garbage collection. And if we remove that pointer, we would just write point blank, save it as white, and then we have to scan it again anyway.
So
just to save the work later on in the garbage.
First of all, I don't have a right barrier on the roots. I never have this. So I will not be able to do this. But if I had the right barrier on the root, then they change all the time. So I mark it black, I mark it white. It's not clear how it goes farther down.
Later on, because when you do the garbage collection and you see the object, you know that all children can also be black, and then you won't have to go over part of the subgraph.
Right. So that's close. I mean, there will be an optimization related to what you're suggesting. Yeah, like looking at these objects that we know are alive. This is something that was done later. So it's another excellent question. We'll talk about it. Okay. So this is the algorithm. So in terms of correctness, after the mark phase, the subgraph that's colored gray, all this subgraph of a node is colored gray, and all the objects with no external references, all the reference counts reflect only external references. I decrement each reference count for each internal reference. And so I have this after the mark. During the scan phase, objects with no external references become white, and objects with external references and all their descendants become black, and the reference counts are restored for them and their children. Finally, white objects after the scan are unreachable and can be reclaimed. So it is correct. We can trust it. And the property is that it reclaims unreachable cyclic structure, but also everything that's reachable from it. So if all of this is white in my traversals, this will also be white. Nothing will mark it black again. Okay? And the advantage is that each cyclic structure is discovered immediately when it's created. So a cyclic structure loses an edge, it becomes a candidate, I test it, find it's a cyclic unreachable structure, and I reclaim all the objects in it. So great. So I have these advantages. In terms of complexity, I have 3 local traces over the subgraph. And like you said, it may become 4 if I have these terrible things that I'm going through a long list of objects and I mark them white, and then I discover that they're actually reachable and I mark them black. So it's even 4 in a worst case scenario. Usually I will not have this, but in a worst case scenario, I will have 4 scans over the subgraph of a candidate. So yeah, I said how, but you said it already, so I will not ask you again. But the main question is how large is the subgraph, and there are not many studies about it. you can say usually what will happen is that you have lots of candidates that have a very small subgraph, like, several nodes, which will be very easy to do. But there will be one or two candidates that will have a large subgraph below them, and doing that will take time. Not comparable to the entire heap. I'm talking about normal benchmarks, but you will need to scan, maybe 10,000 objects in this subgraph. So it's not negligible, the cost of what you have to do in practice. Okay, so let's look at this, how it looks. So suppose you have a candidate. This is the subgraph. Okay, this is a very raw drawing, but this is a subgraph of this candidate. And here are some external edges, and so their subgraph should come out black. The original, whatever is not under external edges, should remain white and be reclaimed. And the question is, what happens if the candidate has an external edge and it is accessible by an external edge? What will happen here? Exactly, everything will become black. If there is an external edge to the candidate, everything will become black and will collect nothing. Okay? Doesn't make sense? These two have here in external. What? They might be reclaimed or not. It doesn't, because they're not related to the subgraph. But in the subgraph, I'm sure nothing will be reclaimed if the candidate has a external pointer. Okay. What if an object has an external pointer, but the pointer is in an object that belongs to another unreachable cycle? So let's say we have this cycle, and now there is an external object that points to this cycle. Okay, now this is my candidate. What will happen? Yeah. Right, exactly. Excellent. So I didn't think, but you're right. It couldn't happen in this setting. It will soon be possible when we do the real setting in which we work. But as we defined it here, this could not be an unreachable cycle, because when it was created, we would have reclaimed it. But if we hadn't reclaimed it, then we work on this candidate, we'll just not be able to reclaim anything because it has an external edge. But what will happen later is when we go to a candidate from this cycle, we will reclaim this cycle and also this cycle, because they're all become white at the end. Okay, cool. And last, suppose the object at the top had reference count 0. Would it make a problem? And I'm asking this, but you cannot answer this because it would take too much time to actually look at the entire algorithm and see that it works well, but it does work well. So what will happen is I'll just traverse this graph. The top thing is actually free. I can reclaim it immediately, but if I don't, then I can go through it and just do these traversals and find out. It will also stay white. There will be no external reference to it, so I will be able to reclaim like that. In general, if my reference counting algorithm got rid of this object, then it would recursively goes to its children, and then any child would get a decrement. And if it doesn't go down to 0, each of the children will be a candidate and will be checked by the algorithm. But in general, we're going to have a similar situation soon in one of the algorithms. So I just want to prepare for that. But in general, it's okay. It doesn't matter if it is 0 or not. I can always take a candidate and check it. I can also check it and get good results, even if I just choose arbitrarily at random any vertex, any object in my heap. I can go on and check its subgraph, and I will see if something is reachable or unreachable from the outside. Yeah. Right, right. We will not do this in our setting, but I'm saying if you did, just look at it as candidate and run the algorithm will work well. And in general, you can choose any node, any object in your heap, and try it. See if it's part of a cycle. Okay, cool. Okay, so in 2 years later, Linz, one of the authors of the previous algorithm, said, this is too inefficient. Let's do it lazily, as we often do. So what does it mean lazily? Many times I decrement a reference count, but I don't get really an unreachable cycle. So it is a ways to check all these candidates. So what I can do is I keep a list of all the candidates. So I don't try each candidate that I get. I just make a list of them. And periodically I check candidates and I can remove candidates if they become garbage, like if they're unreachable, then I don't need to check them. I can just reclaim them. I can check them, but I don't need to. And if a reference count is incremented after I put it in the list, then it is reachable. It cannot be incremented if it's not reachable. So I can put it as a candidate and out of candidacy, back and forth if reference count is incremented and decremented for it. So if the last thing that happened is that the reference count was incremented, it's not a candidate. Okay. Okay, so let's do a break here and at 30 come back. I think I've made the home exercise available. Please check. And I've uploaded this presentation. If you want to re-download, please check. And then I can... Okay. We have the exercise. Did anybody check or do? It's okay, good. And whoever wanted to download the presentation made it, and I can start. Okay. You just remember all the new nodes, and they become candidates. So this is a bad thing because there's lots of new nodes, and they all become candidates. So remember this. And solution one, you could do a write barrier on the roots, and then you don't need to take special care of these new nodes. But this is very costly. So what you do is you just keep all these new objects, and also you keep a list of everything that was referenced by the roots in the previous collection, and these are also candidates for the current collection. So then you're careful enough and you know that everything will be, yeah. Sure, the lazy method always helps, but in this case, you'll just get this, you'll not get these as candidates, and then it will be orthogonal. The lazy thing will help you to reduce a lot of the candidates, but new objects, you have to check them independently of whether you saw something decremented from them or not. Yeah. You're right that if you saw something incremented, the latest thing was an increment, then you don't need to look at them. Yeah. Okay. Why does it make progress? So the following objects are candidates, objects created since the last connection, roots reference to previous collection. So what you know is if there is a new cycle, how can you miss it? That my worry is to not reclaim a cycle. So so we have several cases. If there is a new object in the cycle, I will surely notice it because this new object is a candidate, and then I will see that it's in cycle that's unreachable. Okay, so if there's no new objects, so all objects are old. So if one of them was referenced by roots in the previous collection, then I will also notice it because these are candidates. So this is case 2a. If he was referenced by the roots, they're all old, but one of them was referenced by the roots in the previous collection, I will find this cyclic unreachable structure. But if all of them are old and none of them was referenced by the roots, then there was a cycle in the previous collection, and now this cycle is unreachable. So if it was unreachable in the previous collection, I should have reclaimed it then. If I did not, if it was created since then it's not that it lost a root since then and there are no new objects, it existed in the previous collection. Then there has to be a reference it lost between the two snapshots, and that I will see as a decremented reference. Okay, so this just claims that any cycle that is created between the snapshots, I will see it and I will reclaim it. Okay. And this is in this work of David Rajan, they made this beautiful slide. So let's look at them as a like example of how it works. So I have all these live data, and at some point, these lose references and they become candidates. This is the candidate buffer. And these are acyclic, so I don't even look at them when I do when I do the cycle collection. So I go to the first thing, I mark gray. So I want to mark gray going through all of them. I start with this. I mark it gray, I look at its child and its only child, and I decrement the reference count because it's an internal edge, and I mark it gray. It doesn't have any children, so I can go to the next node, and I mark it gray, and I'm going to its child. It also has only one child. I decrement the reference count, and I go through its children. So I'm done with that. I'm going through its child. It has two children. This is one child that I decrement the reference count for, and this is another child that I decrement the reference count for. And I think I'm done with that. So I can go to this one, and I make it gray. It has two children, so I have to decrement the reference count of one child and the other child, and I'm done with the marking, the first phase. So everything is gray, and the reference counts reflect only external pointers. And as you can see, this is alive, it has an external pointer, and the rest are not. So I go through the scan, where I want to restore live objects and mark white the other objects. And so this one I see is 1, it's not 0, so it's black. And I go to its child and restore the reference count for this edge. And I'm done with this, I'm done with this. And then I go here and I see it's 0, so I can mark it white. And I don't restore reference count for those that are white. I just go on marking their children white. So I go to its child, I see it's 0, so I mark it white. I go to its child and see that it's black, so I don't continue. This guy is reachable, I don't touch it. This is not this is not an edge that will remain in the graph, so I don't increment the reference count of the child. So I just see that it's black and I continue. I go to this one. This is 0, so I make it white. It has two children, but they're already white, so I don't need to restore reference counts or change colors, and I'm done. So now I know that I can collect the white, so I start With this one, it's not white, so I can just ignore it. I go to this one, it's white, and it's children. I go here, it's white, I reclaim it. I go here, I stop, it's black. Then I can go to this one, and I'm done with the algorithm. Okay, this is just an illustration. Any questions? Yeah.
So for the last left type that you wrote, so the roots there would be the previous with the roots at the last left you wrote, or the new plus previous.
Let's give them names. So this will be k minus 2, this will be k minus 1, and this will be k.
So in step, let's say k, so
Okay.
you have the new plus previous, you have the new that was accumulated from k minus 1.
All the new pointers here, yes.
And the previous ones were the new for k minus 1.
Between these two, I don't keep the list of new objects that were here.
At k, you said you have the previous roots from step k minus 1 plus
Right.
the new accumulated ones between the window.
So new objects and old roots, I can call them new objects and old,
On the heap or the new roots?
the new objects that were allocated on the heap.
Okay, so
I have a list of all
you
those.
were saying that old roots and new roots, but no, just roots.
Right, exactly. This is unrelated. Like I have all the roots that were in snapshot k minus 1, and I have all the list of objects that were allocated between snapshot k minus 1 and snapshot k.
And all these are candidates.
Yes.
So the newly allocated ones on the heap and roots in general.
Right. So the roots are usually not very many, but new objects could be a lot. So this is something that I would be happy to not have. Yeah.
So we reclaim verbal objects. Like if it was a root of snapshot k minus 1, we check if it has reference code 0, right? We check is it still a root of snapshot k. And if it isn't, then we reclaim it. And we try to reclaim it.
Right. So this is like another optimization. Usually we don't care if it's a root, but you're right that if it's a root, it's alive. If it's a root of snapshot K, it's alive. So we shouldn't be worried about it and we shouldn't check this candidate. And in general, you're right. Any candidate that is pointed by roots, we don't need to check it. But this is an optimization. It's not in the original algorithm. You could, if you reclaimed it before the cycle collection, it became 0 when you reclaimed it, then fine. It's not a good. I mean, you don't need to go through checking it. Okay, cool. So let's go into concurrency. We have concurrent cycle collection. You remember that when we say concurrent, we mean that we run concurrently to the program. We want to do this cycle collection, and we can do either this or this, concurrent or on the fly. And so clearly, if we just take the algorithm as is and run it concurrently, it would not work. By now, you should know that lots of things can create problems. One of them is that I traverse the subgraph 3 times, and if the subgraph is modified, then I will traverse different graphs in each time. And I think, the counts may be outdated. So here is an example. Suppose I have this as a candidate, and I just begin by tracing it. I do the first marking thing, mark it gray, and then make this child decrement the reference count, and then I recursively go to this child and make it gray and make its child decrement reference count. And then I go like a DFS style. I go to the children I got here. And I also make this gray and decrement the reference count. And then I go to this guy and decrement the reference count from this. And then I finish the DFS. No, sorry, I do this, and then I decrement this one to 0. And now I in this position, the program comes and removes this pointer, right? This is basically terrible. You see, I've done with the marking thing, everything is gray, and these are the external edges. I see ones here, but just someone comes here, the program, and it can change the graph. So it's remove the reference here. Now I do the scan, and so this is 0, so it becomes white. And then I go to the child and I see that it's 1, so it's black. And then I have to go here and I see that it's 0, so I make it white. And I think I'm done with the scan. And if you look at it, you know, A and B, none of it should be reclaimed because it's reachable from the outside. So I reclaim these two. These remain gray. They should be black for the things to go on properly. And the reference count of the reference count is not correct. This one should be 2 and it's 1. So everything goes wrong if we just let the program work concurrently. So we need to do something. We know that. We've seen concurrent algorithms. So the first on-the-fly cycle collector was by Bacon and Rajan, 2001. And so what they do is like, we're not going to get into their algorithm. It was complicated, and what they do is they repeat scanning. If they decide that that something is a cyclic structure, then they don't complete the decision. They don't act on it and reclaim all of it. They wait for the next collection to make sure that it is a unreachable cycle. So they have repeated scanning to make sure that it is really a cycle. They have, I think, 7 colors in their algorithms to make sure they can test everything appropriately. And they have these additional tests which take time, and eventually there's no guarantee that you will eventually reclaim a cycle, because you may suspect that something is a cycle, you check it the next time and it doesn't look like a cycle, and it may remain forever. It's very unlikely that it will happen, but theoretically it doesn't make progress. So this is the disadvantage is that practically you have to do this repeated traversal and it takes time, and theoretically you're not sure to make progress and reclaim the cycles. And the cause is that you repeat the traversals on changing graphs, and so you have a problem. And so we joined forces together, and what we did is we did the cycle collection on a snapshot. When you're working on a snapshot, it's stable. You don't have to check again and again if it is a cycle or not. You just see the snapshot, and if there's a cycle there, then it's clearly unreachable cycle will not be changed anymore. You can reclaim all the nodes in it. So this was the basic idea. So the idea is to use a snapshot, and using a snapshot, we know how to do it. We know before you change an object in the write barrier, you make a copy of the previous version of this node. This is what we did for the reference counting, and given a snapshot, you can use this serial algorithm that we described previously, just run it on the snapshot and see if there are cycles. So you collect all kinds of candidates from decrements of a reference count, and then you check them on the snapshot. If it's unreachable cycle, then you can reclaim it. So all unreachable cycles can be reclaimed, and of course you don't reclaim something that's not an unreachable cycle. So that's what's good about it. And they use the same algorithm, the same write barrier of the Levanoni Petrank. So you can do it the same with the reference counting. You use the same mechanism. You get a snapshot. you update the reference count. If you see a decrement not to 0, you make it a candidate, and then you can do the tracing. You can check all your candidates. Um, can we miss and now there is something that comes up, because in this algorithm, if you remember, we do update coalescing, so we lose a lot of decrements. So you remember that if I have a pointer that between two snapshots goes between all these objects, then the original reference counting does decrement this reference count, increment and decrement this reference count, increment and decrement. And in the new reference counting, the update coalescing mechanism, I only decrement the reference count of this. And all these decrements make candidates. So all of these were candidates. I had n-1 candidates in the past, and if I use update coalescing, I only have one candidate. And the question is whether I lose candidates and I will not reclaim the cycles that they are pointing to, right? This is a concern. You understand? Okay, cool. So I have to show you that I will not lose any cycles. I will not miss a cycle because I don't do all the decrements. So, okay, this is, I want to say that this is very good for efficiency. I will miss a lot of the candidates, but I have to know that it's correct when I'm missing all these candidates. Okay, so we need to analyze this. So let's say case one, if the cycle has a young node, we said all the young nodes are candidates, and then we're safe. We will check it. Okay, case two, there are no young nodes. All objects in the cycles are old. And then in the first case, in the previous collection, was one of these nodes directly reachable from the root. That reference was lost, and now it's a cycle. I do keep all the previous roots, and therefore it will also be a candidate. So I only have this case to deal with where the cycle was reachable from external pointers and not roots in the previous time, because I didn't reclaim it the last time. It was not accessible from the roots. It's not new object, so it was there in the previous snapshot, and it was referenced by some external pointer. So if it was in the previous snapshot referenced by external pointer in the heap, not the roots, in the heap, then this pointer was modified, and all these modifications are registered and are going to make me decrement the previous child of this pointer. So I will decrement the reference count of this node as it was in the previous snapshot. And when I do that, I will get a candidate. So so if I have what I'm having this, pointer to a cycle that was lost. So if any of them is new, there will be a candidate. If this was a root, if any of them it's a candidate. But no, in the previous snapshot, it was pointed by something that was not a root. Now, if this was lost, then this pointer was changed between the previous snapshot and the current snapshot. In the current snapshot, it doesn't point to that. So I will look at this pointer because it was modified between the snapshots, and I will decrement the reference count of this guy. So maybe I will lose a lot of decrements, but a decrement to one of the objects in these cycles I must notice. And therefore, one of them will become a candidate, and I will notice this cycle.
Why do you decrement if you change the pointer?
So in update coalescing, yeah, it could have gone through a lot of changes, but the previous snapshot
because it was the first name, and that's what it would.
yeah, it was the one it pointed to in the previous snapshot. That's what I'm decrementing. So I will do this decrement, and I will notice this candidate, and I will reclaim this cycle. Okay, so I will notice these cycles. So I have fewer traced candidates. This is good for me, very good for me. This update coalescing reduces the number of candidates. ignores a lot of pointer modifications, and I have the snapshot view, which simplifies the algorithm. Concurrency is now not an obstacle. I will just traverse the snapshot, and then from there I can do all the existing way to reduce tracing work. I can use lazy tracing. I can trace all candidates simultaneously, right? All the things that we talked about in the serial algorithm in the first hour, I can use them with the snapshot. So this is great. And now all these things that were done to make, so Harel did this to make things work better, like improve performance. So first thing he said, why should we work on the buffer of everything that was decremented through this period? We could work on the buffers that were collected in an older period. So he actually went 3 cycles back, and then he looked at the old candidates. And so when you do that, you may take more time to reclaim cycles, but you give more chance for the candidates to be erased, like maybe to die with reference count 0, or maybe to be incremented so they are taken outside of the candidate list. So this was something that letting candidate mature and looking at old buffers was something that allows you to remove some of the candidates. Another thing is what you mentioned here several times. If I know that something is alive, then I can just ignore them or actually mark them black. So objects that were dirtied recently, so someone changed an object, pointer in an object, it becomes dirty, it goes to the buffer. This object is not going to be part of an unreachable cycle. Objects referenced by the roots, which is what you said previously. Objects appearing in later buffers. So if I am looking at the buffer from a previous snapshots and now it was added to a new buffer, then I shouldn't consider it at the time of 3 cycles ago. So all of these I can just remove from my concern in the current test for cycles. So this is the second thing Harel did. And the third thing he said is what you said, basically, that I might happen to work on traversing all the white objects and then discover that something is black and traverse it again to make it black. So he said, instead of double coloring, I will use the list of, so he didn't actually do what you suggested, which is to look at all the objects that I discovered the reference count was higher than 0. It is interesting to check this, what you suggested, but it's not clear that I have such a list, right? We can think of it, but because I'm decrementing the reference counts for internal edges, but I don't know if I will decrement it again. So it's not clear how I get a list of all the reference counts that are above 0. But let me not get into it. But in any case, in general, this is a good optimization. So I can take everything that I know is black, like all the things that I know that are alive, maybe reachable from the roots, dirty objects, all of these, I can go from them and mark everything black from them before I start marking white. And that's in the spirit of what you suggested is an optimization that RL used. And I will not get into sliding views if you want to do it on the fly. The same manner that we did for mark sweep and reference counting, you can also do here. Let's look at the evaluation. So here he looked at how many candidates were eliminated. And so it was at most 80% of the candidates were eliminated, and at least, what is it, 15%, 8% maybe, but a lot of candidates were eliminated using his methods. So first of all, it was the update coalescing. So we have fewer decrements, and so we have fewer candidates. And then you have newly buffered or dead objects because I take buffered from several cycles ago. And so between the time they became candidates and until now that I come to check them, maybe they were buffered again or they became dead. And so you see here a big reduction in the number of candidates. He compared it to just his additional optimizations to the work of Bacon and Rajan that appeared previously, and he sees, except for a single benchmark, he's getting a lot of benefits. Since we don't have too much time, I don't want to dive into the numbers here, but it's nice benefits from his optimizations. What he did also, so one of the problems in all of these is all these new objects. We have lots of new objects that we have to go through and check as candidates. This is our biggest problem, the new objects. So what he said is, let's have a lot fewer new objects by doing reference counting on the older generation. Use generations. So the younger generation, where we get lots of new objects, will be traced. Mark sweep, copying something. And the older generation, the new objects there are all those that are promoted, and there are not too many of those. And so we have a lot fewer young objects. And so I will not get into what is age-oriented, but if you do that, you do reference counting only for the old part of the heap, then you get an amazingly small work that you need to do. This is the work ratio that he had to do. Sometimes it was almost unnoticeable compared to previous algorithms. So if you do it for the old generation, it's a lot better. And so this is a comparison to you take a reference counting algorithm and you ask which is better, to run a tracing collector to remove the cycles or to run cycle collection. And what you see here is that Mark Sweep does better than the cycle collection. This is it's better by 5 to 10%. If you look at the regular of the entire heap, and it's not generational. Exactly. And if you now go to the generational thing, then you get that it's basically the same market sweep and cycle collection, except when the heap is tight. When the heap is tight, then the cycle collection becomes a lot better because mark sweep needs to go frequently and traverse the entire space, whereas the cycle collection, it just usually traces a small part of the heap. So it becomes better to do cycle collection by 5, 10, or even more percentage, only when the heap is tight. When the heap is not tight, it's the same. Mark sweep and cycle collection will be the same. So, okay, so to conclude, we've seen the basic cycle collection algorithm. We've talked about concurrent cycle collection, and you see in the evaluation that you have a reduction in the tracing. And in crowded heaps, cycle collection does better than mark sweep. Yeah, that's the conclusion. Any questions? Okay, so thank you and see you next week.